Hello and welcome to One Electron Universe, where we convince electrons to do wonderful things for us. In the previous video, we learned how to design an electronic circuit without using any microcontrollers or writing any programs. We chose to build a square wave generator. We followed the design process, made some important engineering decisions, used formulas to calculate the values of the right components to build the circuit. We used a simulator to validate that the calculations that we did were actually giving us the right outcome. At the end of it, we built the actual circuit. We put in LEDs to give us a visual indication of the fact that the circuit is working. However, if we want to validate the waveform generated by the circuit, we will need an oscilloscope. And that's exactly what we are going to do in this video. We will take the same approach as in the last video for the design process. We will identify the system parameters, choose a design, make some decisions around simplicity, accuracy, and performance. The challenge would be to build an oscilloscope in less than 50 lines of Python code. Let's see if we can do it. Everyone knows what an oscilloscope is. It's one of the coolest looking devices in an electronics lab. It's a very powerful tool that allows you to visualize signals. There are many different kinds of oscilloscopes. The one on the left is a bench oscilloscope, and the older ones would normally use a CRT screen. On the right, you have digital oscilloscopes. Digital oscilloscopes use an analog to digital converter to convert the analog waveform into a digital one. As you can see here, the top figure 1 is an analog wave which is sampled at specific point in time and converted into a digital outcome. When we recreate the wave again from the digital outcome, you will notice that there is a small difference in the original wave and the recreated wave. This is what is called as a quantization error. Let's further understand what a quantization error means. Here you see the same waveform, the black line, which is digitized using different number of levels of the digital outcome. In the first picture, we are using a single bit to describe two levels, 0 or 1. Here you can see that when the black signal is below 0, the digital output is 0, and when it is above 0, it's 1. Obviously, we are losing out a lot of information, and the difference, the loss, is shown as the red dotted line. In the middle picture, we are using 2 bits of information. So we are using 4 levels of digital outcomes. And here you will notice that the red dotted lines are smaller, and the blue line, which is the digital outcome, is much closer to the black line. Finally, in the third figure, now we are using 3 bits. So this equates to 8 levels of digital output. And here you will notice that the quantization error is much lower as compared to the previous 2 figures. Now the question is, why can't we just use more number of bits? That's because the more the number of bits you use to describe the output, the more hardware that's needed, the more expensive it is, and the more time it takes, and the more complex the circuitry is. So how can a microbit help us? The microbit, also known as a BBC microbit, is a pocket-sized computer, and it has many sensors built in. If the name sounds familiar, that's because it is. It is the same organization, BBC, and some of you might recollect the BBC Micro. As the focus is on kids' education, a lot of effort has gone in to build a platform which is easily programmable. Let's take a quick look at the specs of the microbit. We'll be looking at the version 1.3 of the microbit. The main processor on this microbit is a Nordic Semiconductor NRF51. This processor is an ARM Cortex M0 32-bit. The processor has about 256 KB of ROM, 16 KB of RAM, and runs at 16 MHz. The newer version of the microbit has a NRF52, which is a bit more beefier than this one. The microbit has many sensors on board, like the accelerometer, the magnetometer, and so on. What we are interested in is the analog to digital converter. To understand the analog to digital converter a bit better, let's look at the product specification of the NRF51. Here, it says that the analog to digital converter supports three different resolutions: 8-bit, 9-bit, and 10 bits. Unfortunately, the software stack of the microbit that we will be using today hardcodes the resolution to 10 bits. So that's what we are going to use today. In the future videos, we will explore how to change the resolution to 8 and 9 bits. Another key parameter that impacts the accuracy of the measurement is the reference voltage. The NRF51 gives us multiple ways of using a reference voltage. Again, this is not a topic for this video and we will explore it in the future. We already saw the improvement that we can get in the accuracy by increasing the number of bits of resolution. Here, let's look at the cost of that accuracy. As the number of bits of resolution increase, the time taken to measure a sample increases. For 10 bits, the time taken is 68 microseconds. For 9 bits, it is 36 microseconds. And for 8 bits, it's only 20 microseconds. You will notice that effectively the time taken roughly doubles for every bit of addition to the resolution. Another important parameter that we will have to consider for our design is the speed at which the microbit will communicate to our computer. The microbit communicates with the computer using a USB as a serial port, and the speed is 115,200 bits per second. Let's go back and have a quick look at the pinout of the microbit. There are three important pins that we are interested in. The P0, which is where we will connect our signal to be measured, the ground, which is going to be the common ground, and the 3 voltage reference. Now the 3 volt reference, as we will see, is not necessarily exactly 3 volts. However, the important part is that whenever the signal is equal to whatever the voltage is at the 3 volt pin, the output will be 1023, or the maximum value for a 10-bit resolution. The microbit software stack has multiple layers, and this will add a bit of a performance penalty, as we will see later. The bottom is the SDK provided by Nordic Semiconductors for NRF51. ARM has built a common ARM SDK for all its ARM microcontrollers, which is called ARM Embed. This has an online environment, which is pretty amazing. On top of it, we have a layer which is a device abstraction layer built specifically for the microbit. This is done by the Lancaster University. And on top of that, we have the various development environments which are available. You could use the block editor, which is very similar to Scratch, or JavaScript, or MicroPython, or even C and C++. Let's look at the design parameters. The reference voltage is 3 volts, the 3 volt pin that you saw on the microbit. However, when it's powered from a USB, the 3 volt pin actually is at 3.22 volts. The resolution bits, as supported by NRF51, is 8, 9, and 10 bits. The microbit platform that we are going to use hard codes it to 10 bits, so that's what is going to be relevant for us today. What this also means is the resolution, that is the volts that you would see, the minimum resolution per every single jump is, for 8 it's 11.7 millivolts, and for 10 bits it's 2.9 millivolts, so which is a good thing. It's a much better resolution. The sampling time, as we saw, roughly doubles for every single bit. So for 8 bits it's 20, for 9 bits it's 36, and for 10 bits it's 68 microseconds. What this means is the sampling frequency, or the number of samples that you take every second. For 8 bits it's 50,000 samples per second, whereas for 10 bits it's only 14,700 samples per second. KSPS is kilo samples per second. Now there is a number called the Nyquist rate, which basically says that For you to reproduce the sampled wave accurately, you need the sampling frequency should at least be twice as much as the frequency of the signal. Now this, of course, is a theoretical limit. So of course what it means is that if we have our signal wave cannot have, or should, if we want a good representation of the signal wave on the oscilloscope screen, the signal frequency should not be more than 7.3 kilohertz. Now this works well when we have kind of a continuous sine wave kind of a signal. If it is something like a square wave, normally you would need the signal frequency would be 1/3 or 1/4 of the actual sampling frequency. However, this is still not an issue for us. The bigger bottleneck is the speed at which the microbit communicates with our computer. The UART baud rate, which is basically the serial bus baud rate, is 115,200 bits per second, right? So you need to divide it by 8 to get bytes per second. And this is when you're sending 1 byte at a time. Now, of course, if you were to use 10 bits, that means even if you are using, even if you are packing the bits correctly, you still will be sending more than 1 bit per sample. In fact, the platform that we are going to use today, it sends data across as ASCII, which would basically mean we will end up sending 3 to 4 bytes for every sample taken. Let's quickly jump over to the coding aspects and quickly see how we are going to build the oscilloscope. This development environment provided by the microbit organization, and as you can see, it's a very simple interface. Let's quickly look at how we can build our oscilloscope. Now what you can do is you can always go and do a new project, and you need to just give it a name. So we'll say oscilloscope, and that's it. It brings up the interface. Now on the left you will see the microbit simulator, so whatever code you write here will be simulated here. You have a choice of using blocks or JavaScript or microbits version of Python. This is slightly different than the MicroPython interface, which is also available. So this is a bit different. In fact, to keep things really simple, we are just going to use the blocks version. Yeah, it's that simple. We can just use the blocks version to build our oscilloscope. Okay, so in fact, all we need to do here is, we'll remove this. Okay, on the left what you see, and I won't go into details of it, but on the left are all the possible commands available for the microbit. And what you're going to do is, first, whenever the button A is pressed, right, first thing you're going to do is you are actually going to sample the value on pin 0. Now, the value returned by pin 0 has to be put in a variable, so you can either put it on a variable, or to make things simple and fast, we can simply send it out to the serial line. That's it. This is all you need to sample using the microbit and send the data to our software running on the computer to display it on the screen. I have run some performance tests using this platform, and as you can see, at least the analog to digital converter actually has a pretty decent speed. This is very close to the 14,700 samples per second that we were expecting, but it's about 12,195. Again, we will lose out some performance because of the multiple layers that are there, right? You can also do a digital read and write, which basically means it just tells you if the value is above a certain voltage or not. Interestingly, it's a bit slower than the analog, and my guess is that's because it first does an analog sampling of the signal and then converts it into a digital output and sends it out. So we will not be using this. We'll simply use the analog read speed. However, the bigger bottleneck is here, as we were fearing. So if we send out 1 byte for every sample taken, we can achieve a maximum speed of only 5,500 samples per second. But as we know, we have 10-bit data. So either we reduce that 10-bit data to 8-bit, so force fit it into 1 byte and send it out, or we actually just send the data as ASCII as we have received. In that scenario, and again, to keep things simple, that's what this scenario is. And you will notice that the maximum speed of sending data across, or the maximum samples per second that we can have, is around 2,000 samples per second. So now you probably realize, and if you go back to the previous video, you realize that designing an electronic system can be difficult, can be easy and can be difficult at the same time. And there are various parameters that you really need to look at before you actually design your system. Now, for the current scenario, because it's a proof of concept and we just want to see if our oscilloscope is going to work or not, the first thing that we will do is we will simply use whatever is available by default and keep it as simple as possible. This is the Python program that I have written on my computer to interface with the microbit. I'm using two libraries. One, PySerial, which allows the program to get data from the USB connected to the microbit. And second is matplotlib, which is a graphing library, a very well-known graphing library for Python. The code is very simple. If you see the first function there, get data, it's connecting to the USB device on my computer and it's reading a line of data at a time. Now, if you remember from the microbit, every time we read an analog input, we send it out as one line of data. The rest of the code, as you can see, is very straightforward, and all it's doing is taking this data and displaying it on the screen as if it were a graph. And that's it. Just as you can see, it's less than 50 lines of code. There's a lot of comments in this and there are a lot of blank lines. But just in less than 50 lines of code, let's see what we have achieved. This is the output of the simulator that we tried in the last video. And we expect to see the waveform as seen on the bottom of the screen between the microbit pin 0 and the microbit ground pins. On the actual breadboard, the red crocodile clip is connected to the top of the collector, the microbit pin 0, and the black crocodile clip is connected to the ground. I have downloaded the microbit code onto the microbit via the USB interface. To confirm that the data is coming over the USB, first we'll use a utility called screen to check the data on the serial port. And as you can see, we are receiving numbers on the serial port. This confirms the fact that our microbit code is working fine. Now, let's run our oscilloscope UI code that we have written in Python, which uses the matplotlib library to show the graph on the screen and see if we are generating the waveform as expected from the simulator. I'm pressing the A button now and beautiful, we did it. The waveform is very similar to what we saw on the simulator. There is, of course, a performance issue. It looks like it's very slow. Let's see what we can do. We go back to the code. Now, the number here that you see, 1200, that's the number of samples I'm displaying on the screen at a time. Let's reduce this a bit. Let's make it a smaller number and let's see if that improves the performance. Now, of course, as we had discussed earlier, we do know that the sample collection rate is very, very slow. And yes, of course, the wave is now much smoother and much faster. But I think there is definitely more scope for optimization. Let's see what more we can do to make this better. I have taken the analog output and I have force fit it into 3 bytes of data, or so the values, I'm forcing the values between 100 and 999. Now this does two things. One is it makes our protocol much simpler, right? The receiving end, the display software only has to look at 3 bytes at a time. So it can read 3 bytes at a time from the screen, from the serial interface and display it to us. What we lose out here, of course, is the resolution. And in fact, that's the compromise we are making here, to make things a bit easier and faster, but giving up somewhat on the accuracy and the resolution. I have modified the Python code for the UI to be able to handle the optimized data coming from the microbit. Now it will look at 3 bytes of data and there is no new line character at all. Let's see how this code performs. We expect to see a much more smoother curve with a lot more samples per second. Now, you may not be able to see the exact samples per second here right now, but what you will see is that the wave is much wider, which basically means that we are now displaying a lot more samples for a given period as compared to the earlier one where the waves the square wave was much narrower. That's because we were displaying much fewer samples for the given amount of time. I have further optimized this code to be able to send only a single byte of data per sample, and let's see how that code performs. I have not only changed the microbit code, but I have also changed the UI code, and now the UI code will also try and measure the sampling frequency and the frequency of the wave being displayed on the screen. So if you look at the top right corner, the WF is the wave frequency, and it's around 2 Hertz, which is 2 cycles per second, which is very close to 1.9, I think, that we were expecting based on the simulator results. And the sampling speed, if you see, is around 3200, which is also much better than the 2000 that we were expecting earlier, right? I have also added a save option so that you can save the data that is coming in and analyze it later. And I've also done added some UI capability so you can freeze the wave and observe it, kind of study it a bit more. That's it for today. Thank you for watching. Hope you enjoyed the video. This is the One Electron Universe. Bye and take care. See you next time.